Ho students, Mr. Kaczynski with you. We're going to go through problem 4.4 in Thinking with Mathematical Models. It's about measuring variability, specifically standard deviation. All right, first thing, okay, so we're only looking at one variable today. These are the heights of a bunch of students, 16 I believe, and we're going to make a line plot showing the distribution of the data, showing how spread out it is. If I only start at 56 and go by ones on this line plot, 56, 57, 58, 59, 60, 61, 62, that won't be enough to get to 68. So instead, what I'm going to do is start at 56, and I'm going to go by twos. So just like any graph, scaling is the first thing that you want to concentrate on. All right. And I'll even add a label down here. Height measured in inches. All right, and then we're just going to put an X above each mark for how many students are that height. So 56, there we go. There are two 57s, and I'm taking careful precaution to make sure that the X's are the same size. 58, just one. 59, just one. 60, three students were 60 tall, 60 inches tall. So I want to give this feel, don't write this down, but of a bar graph here where these are the same height. So it might be easier to do with lines like that that are parallel to the original line down here. Let's see, so now 62, just the one. 64, I've got two students that are that tall. 66, just the one student. 67, three students, 1, 2, 3. And 68, just the one student. So what we end up is getting kind of a bar graph of sorts. Oops, don't want to do that. So we can see the distribution of the data. Let me show you this real quick. We'll probably use this data later anyway. I'm going to put this data in here. 56, using the calculator, 57, 57, 58, 59, three students that are 60. Got the 62, the 64, 64, 66. Three students who are 67 inches tall, and the tallest student in class, 68. So one thing you can do on the calculator is it's actually not a bar graph, it's called a histograph or a histogram. It's this option right here. So it only uses one variable. That's where my data is, L1. And I'm going to start this at 56. I'm going to go up to 68. I want my distribution to be scaled by ones. That's how I scaled this. Really, it is scaled by ones because we know exactly where 57 is. Start this at 0, and I'm just going to go up to a maximum of like 5. There we go. And what we get, see, here's a histogram that basically shows the same thing. There's the one student that's 56, the two that are 57, there's the three that are 60, and the three that are 67. You notice I'm missing my 68. Maybe I need to go to the window and take this up to 69. There it is. All right, let's move on. Calculate the summary statistics below and explain what each number says about the distribution of heights. Yeah, let's do that. So the range is the tallest minus the shortest, which is 12 inches. And let's add a little explanation to this. The difference between the tallest student and the shortest is 12 inches. All right, what about the mean? That's where we add up all the numbers and divide by how many there are. So Let's write that down. We'll go sum of heights divided by a number of students. All right, so let's add these up. I'll show you some shortcuts here. We've got the 56, the 2 students, so I'm going to do 2 times the 57 plus the 58 plus the 59 plus the 3 students that are 60 inches tall plus the 62-inch tall plus the 2 times 64 plus the 66 plus the 3 times 67 plus the 68-inch tall student. That's 992. I remember doing this yesterday, and I think I've got the right number there. There are 16 students, so if we just do 992 divided by 16, we get 62. All right. Let's do this too. Let's add an explanation for that. Let's say the average, let's put that in quotations because there's more than one kind of average. Student height is 62 inches. Didn't finish writing my answer, did I? 62 inches. I want to show you this too in the calculator. If I go stat, calculate, one variable stats right here, option number 1, and I run that for list 1, you can see the very top number is 62. So that's my average right there. You can also see the second number, 992. That's the sum of my numbers, and you can see n equals 16. That's the number of pieces of data that I put in this list. Remember when I entered that numbers in? So it's one var stats, real great way to shortcut that stuff. All right, what about mean absolute deviation? Well, with mean absolute deviation, what I have to do is I have to subtract all of these numbers from the mean, 62. What I think I'll do is I'm going to do that up here. So like 62, and even then I look for the difference and I ignore whether it's positive or negative. So 62 minus 56 is 6. 62 minus 57 is 5. 62 minus 57 is 5. 62 minus 58 is 4. Minus 59 is 3. 62 minus 60 is 2. 62 minus 62 is 0. Now 62 minus 64 is negative 2, but I'm going to ignore the negative and just call it positive 2. 62 minus 66 is negative 4. 62 minus 67 is negative 5, but again, ignoring the negatives. 62 minus 68 is negative 6. So the mean absolute deviation would be the sum of all these numbers divided by 16. I'm going to cheat again. How about this? Let's go up to L2. I'm going to do 62. Actually, I'm going to do this. I'm going to do math number. Option number 1 is the absolute value. I'm going to do the absolute value of whatever is in list 1. So I hit second 1 minus, actually, no, it doesn't really matter, but 62 minus whatever is in list 1. So the absolute value of the mean minus the data. And there's all those numbers. So then when I run stat, calculate one var stats for list 2, I mean, obviously I could just use a calculator and add all these up, okay? I end up getting a sum of 58, obviously divided by 16. And 58 divided by 16 is 3.625. So, and let's put this explanation. Most students are within 3.625 inches of the mean. That's kind of what that means. So this is how far away the students are from the mean, shortest person and the tallest person, 6 inches away. And then we kind of average, what's their average distance from the mean? Maybe we should put that. Let's do that. The average difference from the mean is 3.625 inches. There we go. All right, let's move on to the next thing here. Like the MAD, you calculate standard deviation of a set of data from the differences between data values and the mean. To calculate the standard deviation for the following height data, complete the following steps. 1, find the difference of each data value and the mean. We just did that. So I'm going to do it again. I'm just going to write these numbers real quick. But notice they're not ignoring the negative. So 59 minus, or 62 minus, 59 minus 62 is negative 3. 60 minus 62 is negative 2. 62 minus 62 is 0. 64 minus 62 is 2. 66 minus 62 is 4. 67 minus 62 is 5. And 68 minus 62 is 6. All right, so check. We did that in green. Square each difference. So now I'm going to square these numbers. Negative 5 times negative 5 is 25. Negative 4 times negative 4 is 16. Negative 3 times negative 3 is 9. Negative 2 times negative 2 is 4. 0 squared is 0. 2 squared is 4. 4 squared is 16. 5 squared is 25. And 6 squared is 36. There, I squared each difference. Add the squared numbers. Okay, I could do this with a calculator. Let's go edit. Those are all I got to do is square all these numbers. So if I just go second L2 squared, boom, it squares all those numbers. When I go stat, calculate one variable stats for list 3, it's going to give me the sum of all those numbers, which is 258. 258. Again, I could have just taken a normal calculator. I know I'm making this more tough. 36 plus 25 plus 25 plus 16 plus. Kind of pointless to do a shortcut when you end up doing things the long way anyway. Three 25s. $258. There it is. Okay. Divide by n minus 1, with n being the number of students. So all I got to do is 258 divided by 16 minus 1, or just 258 divided by 16, or 15, which is 17.2. That number is called the variance. And then find the square root of the variance. Square root of 17.2. You just hit second x squared button, 17.2. This is the standard deviation, about 4.1. 4.1. We'll talk more about what standard deviations are in a second. It's kind of like mean absolute deviation. Remember that 3.625 we got? This time we get 4.1. By the way, stat, calculate, one var stats. Let's see. Oh, wait. Let's go stat, calculate one var stats for list 1, the heights. And see that 4.147? There it is. That's the standard deviation. So the calculator will do it for us. All right, moving on. Each dot plot shows the distribution, mean, and standard deviation of heights of 20 athletes. The 20 athletes are a random sample of volleyball players, basketball players, and gymnasts. Interesting data. Okay. Compare the heights of volleyball players to the heights of basketball players. What can you say about the similarities and differences of the dot plots? Volleyball players and basketball players. Well, they're all very tall. In fact, they have the same mean. But notice that the volleyball players are closer to the same heights, whereas the basketball players are more spread out. And the standard deviation is the measure of how spread out the data is. So let's write something down here first, and then I'll go more into that. So how about this? How about both teams have very tall players on average, as shown by the mean, but the heights of basketball players are more spread out, as shown by the standard deviation. I'll fix this in a second. All right, so let's do this. Let's go with the mean. I'm going to do this in green. Let's do it in red. The mean is 78. So that would be right here. Okay, the standard deviation is let's use a different color. Let's use purple. The standard deviation is 2.38. So watch this. Let's go 78 plus 2.38. That would be 80.38. Where's 80.38? Right about here. And then let's add another 2.38. And we get 82.76. That's about right here. Now let's take the mean 78 and subtract 2.38. 75.62. Where's that? Right about here. Yeah, I can do better than that. And then we'll subtract another 2.38. 73.24, which is right about here. Okay. So most of the data, you can see it falls within 2 standard deviations of the mean. I would call this number right here, let's get a new color, how about pink, an outlier. So anything that falls outside of 2 standard deviations is an outlier. So a standard deviation is the measure of the spread. Let's do that same thing again with the basketball players. So we know the mean is 78, that's right here. And then the standard deviation is 3.77. Let's look at that. 78 plus 3.77. 81.77, just shy of 82. And then if we add another 3.77, 85.54, which is right about here. All right, let's take the mean 78 and subtract the standard deviation. 74.23 is right about here. And then we'll subtract another 3.77, and that's 70.46, which is right about here. So again, we do have an outlier. We got a libero, if you know those volleyball players, probably a libero, right? And probably a point guard down here on the basketball team. Okay. Next, compare the gymnasts with the basketball players. What can you say about the similarities and difference? Well, notice that they have a similar standard deviation to the basketball players, but a much smaller mean. So let's put that into words here. Let's say both teams have data that is more spread out than the volleyball players. Spelling volleyball wrong. But the average gymnast is much shorter than the average basketball player. How about that? Let's do that one more time with showing how spread out. 63. This is the average gymnast. Okay, 63 plus 3.77, the standard deviation, gives us 66.77, which is right about here. And then add another 3.77, it gives us a 70.54, which is right about here. So there's really, even though this is the tallest gymnast, he or she is not an outlier in this team, okay? Let's go the other way. 63 minus 3.77 minus 1 standard deviation, 59.23, which is right about here. And then 55.46 when we subtract another one. So notice all of the gymnasts fit within 2 standard deviations of the mean. All of the gymnasts are within 2 standard deviations. No outliers in that group. No outliers. So even though the data is pretty spread out, we don't have any outliers. All right, that's it for this lesson. Have a good one.